Then, so I think.
How did you try to pass how much coffee made?
It's different.
This is the same brand.
that sound back on. There we go. And okay, we can start whenever you guys are ready.
Hi there, welcome to this meetup group for GPDB. We have here today Xin, who worked on the query optimizer, and he's going to talk about what ORCA, the GPDB query optimizer is, and how you can go ahead and hacking query optimizer. So thank you, take it away.
Thank you, Linky. Hi everyone, welcome both in person and also online. Over there. If you have comments, feel free to comment under the YouTube, and we'll have people reading your comments in, and we'll answer it after the presentation. We have a session for Q&A and interactive sessions. Good. I even can make it a name for this presentation. I'm thinking, hey, this is a 101 class for anybody who wants to touch GPORCA. I think something to it. So I call it GPORCA All Access 101. Basically, the GPORCA project is done by the data team in Palo Alto. We open sourced in 2016 January. And the location for the open source is under the GitHub. And you can go there and find the original blog where we announced to the world the first, so far still the only open source query optimizer. In this talk, we'll learn about what's the GPORCA architecture. I hope it's a good information, and why we use the GPORCA, what's the pros and cons comparing to the existing planners, and also how we can contribute back to the GPORCA. Hopefully at the end of the talk, you can get the repo, add a feature, test it, and then provide and make this optimizer even better and benefit the entire community. What is GPORCA? It actually stands for Greenplum Orca. And what is Orca? Orca is basically just a name for this query optimizer, and we also give it multiple different names. In 2015 July, when we released the GPDB 4.3, we call it Pivotal Query Optimizer, PQO. And then in the paper, we just call it Orca in Sigma 2014. Later on, if you go to the code, you will see GPOPT everywhere, and somewhere you'll see GP_OPT, somewhere you will see the folder is GPOPT. They're all referring to the same thing, the query optimizer.
Because we couldn't trademark it.
Okay, outline of this talk. Do some introduction, architecture. We'll do some diagram of the development. We try to the optimizer. And I'll tell you how to do the stuff to get started on the build, the test, and debug it, and then see how we can contribute back. Here's the example. It's very simple, right? We try to find all the the beers actually in San Francisco. In this case, we have two tables. We have bars and cells. And bars is distributed randomly, and cells is distributed by the bar. And you join those two things together, you try to find the bar, find the beer in San Francisco. And when you have this query, when it's running inside a Greenplum cluster, exactly break it down into multiple slices. As you can see, if you do bottom up, we'll have the slice 3, which is looking for all the bars and filter out the city, which is San Francisco. We redistribute the data on the joint column, which is the name. On the other end, the slice 2 can run in parallel and scanning all the cells, and then doing the hash join with the result redistribute about the bars, and project it. At the end, on the master, we collect the data and we return back to the user. If you look at from the query execution point of view, the multiple slices actually have multiple instances on different nodes. And in this case, you will see slice 3, slice 2 actually running in parallel in one segment, and same thing for all the rest of the segments. And all these lines showing the data flows between slices. At the end, we have a gather motion, which is collecting all the data. Now the question is, how can we make sure the query optimizer is good enough, even under such complex class environment, we can get the best play? GPORCA, we published a paper in Sigma 2014, One of the thing or unique feature I feel like it is GPORCA can optimize all the TBCDS queries, all of them. The surface area is very, very wide. And if you look underneath, you will see there are about 90 logical operators, 50 physical operators, 40 different scalar operators, and more than 110 transformation rules to really make it capable to optimize complex data and data decision queries. Here are the few features we see is better than the planner. The first thing is on the partition elimination. We do a better job. We add multi-level partition support, sub-query on nesting. This is crucial for some of the TBCDS query to really return. And common table expressions is very commonly used. Join on possible data types, improve the join order, join aggregate reorder, sort order optimization, and we even can do a skew-aware optimization. Okay, let's take a look at the architecture of the GPORCA. At the very beginning, when we designed the GPORCA, you can see GPORCA is like a standalone library. It's designed to be plugged to any kind of host, And then it defines an XML interface here we call data exchange language to describe what I need in order to optimize. So they break down into XML format for the query, XML format for the metadata, including statistics, everything, and metadata, and XML format about the final plan we generated. So as long as the host can produce and consume the Excel format data, then it can interact with GPORCA, let the GPORCA to optimize the query and execute it. So in this case, for example, for GPDB, we're using the parser from the host, parse the original SQL string, and translate it into the DXL format. Send it to GPORCA. During the optimization, we go through the metadata provider, talk to the host, grabbing all this data information. At the end, we produce the best plan, give it back to the executor, and execute it. So by design, this one can be able to plug in any kind of host if they can providing these three modules. If you look deeper in the GPORCA part, roughly is split into two pieces. There is a layer we call GPOS, which is the Greenplum operating system in that case. It handles about the file IOs, exception handling, concurrency controls, memory management, and then building on top of that is basically a job scheduling based optimizer. Everything is a job, and we finish optimization, we produce the best plan. And all the context information about different credit plans is stored in the memo data structure. I'll have an example to explain the memo later in the slides. And there's a search framework to figure out what should I do in this huge space I just stored. And in terms of optimization rules, there is different operators we can try, logical, physical operators. There are different transformation rules to make equivalent query plans. There's cost model to help me figure out which one is better, which one is worse. Property enforcers is very interesting and unique if you want to make a query plan good for different kinds of hosts. Like in Greenplum, in this case, that's how they sort it. And estimation model to figure out in my base table. And then there's a metadata cache about the data types, what kind of operator we support, and so on and so forth. We'll go through those in details. In general, there is like 5 steps for ORCA to optimize the query plan. We call step 0. It's pre-processing. Basically, at this moment, we are not creating more search spaces. It's still the same plan. We massage this plan to a form where we think it's always, heuristically, it should be always better. For example, a predicate pushdown is happening in the pre-processing. Second is the step 1, which we start to explore all the logical equivalent query plans. That's dealing with the map, And step 2 here, basically we look at the prior plans we have, and we start to acquire the statistics and compute how many cardinalities for, for my join, for my table, for my index scan, so on and so forth. At step 3, once we figure out a good set of plans, we say let's convert them from logical to physical. In step 4, we make this query plan more MPP friendly, massive parallel processing friendly. And in this case, basically look at distribution, what's the easiest way to distribute, what's the best cost to move the data around, and what's the overall costing for it. So if you look at everything before, like from step 1 to 0, 1, 2, 3, you can think of this as a regular single parameter. And the leap is basically having the last step to really make it an MP friendly plan. Here is the example of the step 1. Memo. Memo is actually a compact in-memory data structure to try to store a lot of query plans. Here is the example of a query plan. It's a logical expression. You have 2 tables, T1 and T2. And then we join them together on the condition T1 column A equivalent T2 column B. And then the T1 is on the left-hand side, and T2 is on the right-hand side. So this is the query plan. When this one breaks down into memo, we break it into memo groups. And within each memo group, we have memo expressions. The definition of a group is basically saying all the expressions within this group is semantically equivalent. Right? If they're semantically different, we'll break it down into separate groups. And here, we're indicating inner join depends on group 1 and 2. In turn, we know how we can construct the original plan out of the memo structure. I will show how this one is going to help to store a lot of plans. This is an example about transformation where we can produce semantically equivalent query plans. It's very simple transformation in this case. We have the original join comes in saying T1 is on the left, T2 is on the right, and this is the inner join. So we can apply a transformation rule saying, hey, I can change the order. The result will be the same. Without a memo, I'm going to 2 query plans, make a copy, and just change the expression order. In this case, we basically reuse the group 1 and group 2. Only thing, we add 1 more expression in the group 0. And just switch the order, and that will produce a new plan. So memo is a very good data structure to store a lot of query plans in a very good size of memory. And here basically representing 2 logical expressions. Once we got all the transformation rules applied, memo will be crowded and populated with all possible semantically equivalent plans. Then the next thing I want to know is which one is actually better. Before I can make any judgment, I need to know how many rows we're dealing with. In order to do it, basically the top-down request, looking at the query plan saying, hey, in order to understand what do I need, what statistics information do I need. So from the top down, look at the joins, and join saying, I need to figure out the join cardinalities. In order to do that, I need to know the statistics for A and also the statistics for B. Once the request goes down, the GPORCA talks to a metadata accessor, which is check when we have enough information already retrieved in the metadata cache. If we don't, we'll talk to the host and retrieve those information. For example, when we optimize it down, because we have 2 expressions, we'll see, in this case, I'll check what's the status for A, what's the status for B, and then the first time I'll retrieve it, I'll store them in the cache. Next time I come to the second plan, I want to say, hey, is there anything better than this way? In this case, the metadata is already in the cache. We're not going to talk to the host again to retrieve the stats information. So we'll reuse it. Once we got the statistics information, we do a bottom-up computations. In this case, we have group 2 saying, oh, this is my distribution of my column B, and this is distribution of my column A, and the join said, oh, this is how it looks together with the join candidate. After we have all the statistics, do some basic pruning, and the thing is we're talking about a logical plan, right? We know how this inner join is implemented. It could be a nested loop, it could be a hash join, it could be a merge join. So there has to be a transformation from a logical operator to a physical operator. And that transformation is called implementation. So step 3 basically transform a logical expression into one or more physical expressions. Like inner join can be translated into a hash join, merge join, nest loop join, so on and so forth. Once we have that, we start to pick what's my best plan with my current distribution. And that is done by the MVP optimization through a property enforcement framework. The basic idea is I have sending a request top-down to my pair plan and saying what is the cheapest way I can evaluate it, which is my results satisfy this kind of required properties. In this example, basically I'm saying there's 2 parts of property. One is called distribution property, the other is called order property. Distribution meaning at the end of the execution, how my data will be distributed. We're looking at the end execution, everything should be on master, so it's a singleton. The second one is talking about at the end execution, what kind of order I'm looking at. So in this case, basically saying I want the result to be ordered on T1.A. And this one will start to push down and doing the property derivation and costing. If you know this one is a hash join, then I know I want to have both tables hashed on the join column. In this case, basically I want to say T1 should be hashed on the column A, and T2 should be hashed on the column B. In order to do that, basically propagate the requirements down, because for this expression, I don't care how you get it, but if you can get it, that will be good. So basically, we pass the requirements down saying, hey, for scan T1, I want to hash T1A, I don't care about the order. Same thing for scan T2, I say I want to hash on T2.B, I don't care about the order. And you can see the other results here. If the T1 distributed on the T1.A, there's no further motion, which is meaning I'm going to move my rows around. No further motion is required. However, if the data is actually distributed in a different, say T2 actually distributed on C, and I need to redistribute this one on the column B so that I can join them together. Then there's extra cost of redistribution. Once we figure out the redistribution, there's and this one comes back, so we got this part settled, and we still have one more, which is regarding to the order, right? I want my result in T1.A. So in this case, for the T1.A, I can either do a sort of all the results on the T1.A, and then I do a merge with the order preserving gathering, or I can do a gathering which I don't care about the order, and then sort at the very end. All these variations and costed, and this one will be chosen to return to the host. Okay, that's the overall description about how GPORCA works, what's the layer there, what's the roughly every step, what they do. And next one I'm going to talk about, hey, this is cool, I want to be part of it, I want to contribute, what should I do? With this one, we're going to walk through an example. And in this example, we're trying to add a rule, a transformation rule, which is very common in the MTP environment, saying, I want to do an aggregate. But in order to do this aggregate in the MTP environment, split it into a local aggregate and a global aggregate. Here, the example saying I have three columns A, B, C, I distribute by A. And my query is saying I want to get the sum of C from the pool, which is grouped by B. The general idea behind it is basically saying if we can do all the local aggregates on the segments, which is dramatically reduce the rows, and then we do the global aggregation on the master, then the speed will be optimal for this setting. In order to make that possible, we need to introduce a rule saying if I see a query plan like this, which is this is a group by AGT operator by column B, and I get from table 4, I want to aggregate with the sum of C. That is equivalent. I split the B with the sum. It doesn't hurt. Even in a single node environment, it doesn't hurt. It's just redundant. But even in the MPP environment, you can make this one running on the segment and this one running on the master, and that will speed up the query dramatically. We say, okay, good. Let's add a rule. Every rule in GPORCA is actually encapsulated in its own class. In this case, we'll introduce a new class called C transform split GBAGG, group by aggregate. And all the header file basically go under orca libgbopt include, and the sources is under src. In order to trigger the transformation, we need two parts. One part is I need to identify where am I going to trigger this transformation. That is the pattern matching part. So I give you a tree, I give you a plan. How do I know which part I'm going to apply this rule? The second part is like when am I going to trigger it? That's called precondition check. Here is an example. So the query pattern looks like this. Basically, we're saying this is an expression which is trying to represent a certain pattern like that. And I say I'm looking for a logical group by aggregate. That has to be the expression operator I'm look on the top at the root. Then I'm looking at this one should have one relational child and one scalar project list. In this case, this one, the C pattern tree for the scalar representing the sum C, going to match the sum C. And this one expression for the pattern list going to match the get 4.
We have a question. I was asking how many types of aggregation we have and what is the difference. We can hold this question actually answer that, but
Yeah.
I think it's good.
I can answer it now, and then maybe we can part of the other question at the end of the presentation. We'll do that. So the question is how many times we can apply the aggregates?
How many types of aggregation we have and what is the difference?
Yeah, type of aggregation like a sum, average,
Okay.
standard
We can split
deviation,
anything.
This is aggregate functions.
min, max.
As long as you
Sure. We have stream max and hash max.
So the question is quite odd.
Yeah.
So
Yeah.
you can have local aggregation, you can have intermediate aggregation, and you can have final aggregation. That's just in the abstract sense.
Sure.
You can have different kinds of aggregate functions.
He's asking for phases.
So then
okay.
it is local
Local.
aggregation, intermediate aggregation, and final aggregation. But just to complete my thought, then you can have predefined aggregation like min max, and then you can have user defined aggregation.
Right.
And then to just complete that, we can have stream aggregation, or you can have hash aggregation. So those are physical hash aggregation operators. But anyway, that.
Yep.
But
Thank
basically,
you, Timothy. Yeah.
the aggregate function needs to support splitting. So the ordinary functions don't necessarily, ordinary user-defined functions don't necessarily splitting. But we can talk more at the end.
Yeah. Like sum can be split, count can be split.
Average can be split.
but others may not be able to. If they use a different aggregate, which they don't provide that split.
The user needs to supply like an optional function for us to understand how to split it.
All right. Thank you. Yeah. And then let's park the other question to the QA session. Yeah. Awesome. Okay. So we talk about the pattern. If we only have the pattern, we only solve part of the problem. The other problem is when we're going to kick in this rule. If you look at the pattern, so here's the question about, if I already have a query plan split it, what will happen in this case?
Keep splitting.
It will splitting because it will split this one again. It will match this one, it will split it again. Then we have to have a condition saying, hey, I'm only going to apply this rule if certain condition match. And that's the precondition check. In this case, we say, are my rule actually compatible? So if I know my result is not generated by myself, then I can apply. So this is basically saying, don't recursively, infinitely doing the split. Yeah.
Just to add on, so basically at each step we record who created this operator. So if this ag if it was already fired once, it'll say, hey, this was created by a splitting.
Right.
So we want to truncate that.
Very nice. And after we do the matching, after this one passing the precondition check, then we actually call in the function to do the transformations. All the details will be implemented in this function. It gives us three parameters here. One is the context, like what's the optimization context. I'm going to use information from here. I'll update more information in the context. And this is what is my result at the very end. So if I have two way of doing the aggregate, or if I have a 2-stage or 3-stage, whatever, all the thing will be generated. And this one is basically what's the input expression I'm going to apply my rule out. After we have the rule created, and that one has to be registered to make use of it. And the registration actually in another class called transformation factory. And just adding one more saying, I'm going to create this rule in my factory, then it will be used later on. Okay, let's take a look at the code base. If today you go to GitHub, you download the GPORCA, and this will be the top level folder you're going to look at. CMake is where all our CMake information, because that way we use CMake to build our project. Contours is our continuous integration pipeline information to always check the quality of the code. Data is where we store all the test data. And libgp, dcog, libgpos, the core library that depends on, I have more slides to describe details. The patch is where we have some few changes to GP Xerxes. Scripts and server is where we have our unit test. So if you, from the bottom, remember the architecture of the GPOS is on the bottom. So let's leave GPOS. It's doing all this memory, task gathering, exception handling, and even have our framework for the unit test. So if you look at the code, roughly under the XRC, it's very straightforward. Tell you this one dealing with the memory, this one dealing with the error, this one dealing with the task, this is the test, and then here you have the unit test. Include, then you have this remember DXL, where that is defining the interface between the host and the GPORCA, that is actually here. So you can find all the operators. We do the translation for DXL, the parser, the XML is here. And then this one also contains the statistics. And we have a bunch of ways to control the behavior of the optimizer. We call them trace flags. So you can turn them on and off and controlling what rule on, what rule out, what information do I want to see, so on and so forth. On top of that is the libgpobd, which is actually our engine. It's doing the the search, it does the metadata caching, all the manual data structures here, all the operators are defined here. For example, the walkthrough, when we said a by AGG rule, is going to be put somewhere here. So basically, you can see this is breakdown into the engine, the metadata cache, the mini dump, which is a very interesting thing. We can describe later on to how to use it to test the GPORCA. All the operators here, the search, the transformations, and then, how to say, GPORCA is very modularized. We actually separate the cost model out of the core engine. It's in the GPDB cost. And in that, you can plug in different kind of cost model, depends on your host. In this case, we have two versions of the GPDB cost models, and then we even have another version where people can plug in their own configurations to configure the cost model. Serve all unit tests, which is a very nice feature if you want to contribute back to the GPORCA. You don't even have to run the GPDB. You can actually just compile the ORCA and run it. And this one basically stores all the DXL information we need, which is we can replay inside the optimizer. I think I have an example later on the mini dumps. Okay, then data. So all the test data in the XML format, in the data exchange language, which is XML format, will be stored under the data folder. So that has, the cost, the mini dump, metadata, breakdown into different transformation scenarios, multiple partitioning. Okay. Now you get a clone. You take a look at the structure. You'll understand it. The first thing you're going to do is to build it. And building it is actually very, very simple. You need to get a CMake 3.0 plus, and then we need to have another dependency, which is GPXerces, to handle XML, and you can get from the GitHub location here. Once you build and install the GPXerces, and also install CMake, the rest of them is pretty simple. You just go to the repo, make a build directory, CMake dot, and make it. For the purpose of controlling the quality and making the pipeline, which you to continuous build and run tasks on top of it. So this one basically we build Xerces, and we build ORCA, and we publish it. We build GPDB, we run test.
Actually, we also ran test there.
Unit test is running
We
here.
ran test there. That's actually the bulk of the time.
Right. The C test is actually running here. The unit test running here, and this is more on the integrated once we integrate with the GPDB. Talking about the test. You do anything, you touch it, you modify it, maybe you'll play around with the rules. You don't know whether it's good or bad. So the thing you run is the C test. So this one you can run in 7 threads currently. Or after running all of them, one of them failed. And this is basically telling you I can just run the one which is actually failed and verify. The entire thing finished in less than 2 minutes on this laptop. And the other thing, remember, there's integration test at the end of the pipeline. Thanks to Jesse here. You can go to GitHub and go to this location, and actually you can run a GPDB in the Docker with the version of the GPORCA you're building, and that will run through a bunch of IC install check good tests to make sure it works well with the GPDB. Well file, then how can I figure out how can I figure out where to go? Right. there are multiple things to help diagnostic the issue before we trace down and find all the root causes. One is the traceback.h, which you can go there and see a lot of numbers like this, 101000, 101001, so on and so forth. We're all changing the behavior of the GPORCA. And for the easiness to debug it or narrow down through the GPDB, most of them map to the GUC, the Grand Unified Configuration. So basically, in here you can say, I want to use GPORCA set optimizer on, and I want to actually see the query. The query where the ORCA was. So you turn this one on. And when you run it, you'll actually see the query input. And mini-dump. Mini-dump is one very powerful tool, I believe, as part of GPORCA. And as soon as you get a handle of it, it's very, very useful. First thing is it can create a mini repro for you. Say I have a query, it doesn't produce the plan I want, then what do? You either say I'm always going to run through the GPDB, go through all the troubles, or you do all these commands, and then it will produce a little XML file for you. And that one will have all the metadata, all the input query, and even the output query for you. Then you can just run that D pointing to that data, and then you can just run directly without optimizing, instead of always going through the host. This is more GUCs, which is help you to find, this is just saying I want the message to be on my client. I turn the optimizer on. I want to look at the input and output plan. Here is, remember the memo? In the memo, sometimes you have a lot of plans. And how do I know where the bug is? Is that bug actually in, I didn't actually generate the plan? Or I do generate the plan, but it's not optimal, right? Then enumerating them and really see it is actually a way to verify, yes, I do generate it, and this is what it looks like. And this one even pick the plan search for you. If we want to know more about, I just write a new rule, transformation rule, full, or transformation rule, super optimization. And you want to know how good that thing is used. Did I actually call my rule or not? You can turn on the statistics and see how expensive is my rule, how many times that rule is actually called. And you can also debug into the transformation to say, hey, this is my input, I go through the transformation, this is my output. So it's a very useful set of GUCs. The other thing is actually print out the whole memo. And that sometimes is very valuable information to pick in my search space and see, hey, is there anything wrong? And this will break it down into the stages. Remember, we have the stage 2, stage 1, exploration, and then the implementation where the logical becomes physical, and the last one, the optimization, the MPP, the final step. And if you want to find the root group, it doesn't have to be the first group, and doesn't have to be the last group, just searching for root. This is another very handy tool you can do directly through GPDB, is to turn on and off certain transformation rules. It's very useful if you want to narrow down the scenario to see if that relates to my rule, or is actually unrelated. So you can quickly turn off your new rule or the rule I just changed and see how that thing behaves. This is very funny. The thing in optimizer is it's a scheduler-based, process. Then it doesn't have a call stack, meaning if I apply rule 1 and then apply rule 2, then apply rule 3, you won't see a call stack saying 1, 2, 3, right? In that case, then where should I set breakpoint to really stop it? These are the critical points you can actually stop it on. This is entry point for the entire optimizer. This is where we do the translations from the DXL to the query. This is the pre-processing steps, including predicate pushdown, a lot of things. And here, 2, 3, and 4. Oh, my number is a little bit different. Anyway, all these optimizations are happening here. So for the transformation rules here, this is where we do the final step of enforcement. And then this is the final step where we translate the execution plan back to the DXL and give it back to the host.
You forgot the check required properties too. You can add it next time. Version
Next time.
2. Version 2.
Version 2. Yeah, we should have 102 or 201. Right. Even today, say, hey, I want to contribute. Fantastic. What do? Go to the GitHub, download the GPORCA, look at the issues. Or if you have an issue, you found an issue in the GPORCA in your environment, you can report in the issues. And then hopefully you can fix the issue and send the pull request to us. And this is we have a mailing list, GPDB users plus subscribe at Greenplum, just using the same mailing list. And thank you very much for using and listening. That's pretty much it for the presentation. I think we are reaching the Q&A sessions. And
Oh, thank you.
and actually today, for the people who join a little bit later, I have a lot of people from Query Optimizer team. They are very knowledgeable.
Where are they?
Right. Okay, any question? Is there any more questions online?
No.
Pretty quiet.
So one of the things which so all the debugging stuff you had mentioned, all those knobs.
Right, most knobs I'm mentioning here, they're on the GPDB side. Yeah, so there are all the gugs on the GPDB, which is help you to go to a point where I say, oh, good, I have a good referral, this is my mini dump.
Also, you are giving these as a hint to collect a mini dump, and then you can go in Orca land and play with it.
Exactly. That will be the proper process.
I had a question. So the place where we do the status is derivation, right? So where we see for a particular column, these are the histogram and whatnot.
Correct.
So for instance, I had a table, there was such stat stores for that in the cache. And someone truncated the table, reloaded the data, and now there are new set of stats which are there.
Right.
How does the metadata cache knows that it has been changed, or for the next way I should pull it up from?
I can answer.
Good question.
So Postgres has a system called syscache. And in syscache, we can register callbacks and hooks, meaning that when certain events happen, we can customize what should happen. So one of the things is we hook into syscache, and we will just evacuate the invalidated cache entries. So what you're describing in the general case is how do we invalidate the cache?
Right.
So what we do is we hook into syscache so that we know when things change, we will just evacuate the cache. Yeah. And truncating table is one of them. Inserting is another one. So using syscache.
Currently, DDLs that happen, and forget even what's the definition change, right? But we need to drop that. So as Jesse said, we have a hook that for these commands we just flush the cache out.
It triggers the invalidated cache.
It creates it. Yeah. So currently this is one thing. Currently we throw away all of the cache. So if someone wants to contribute and fix, just
Wait, you're happy?
so if anyone wants to contribute, that's a good first step.
But yeah, cache invalidation is a very hard problem.
Well, do we have any actually place where people can actually know what they can contribute to? Like this one, as you said, is a good place for contribution. But if I want to contribute, but I don't know what I can do at
pain and you think, oh, I wonder if the author can do that for me. I don't. Let me make that happen.
So eventually we are going to have an open tracker, which is all public view. We are not there yet. But up till then, we can report such issues. It's a very good point. We will report these issues in the issue list. We already have some. If you go to the GPDB side, and
Even
if you
here
get,
we have
even
issues.
we have one issue right
Yeah.
now.
Yeah.
But if you go to the GPDB side, let's walk this through.
So before
Maybe
we
we
have
can get
open tracker, people can use GitHub issues as a proxy.
Could we put it on the screen so we can? So if you go here and right now, if you just say assign, just go to assign to me.
This?
Yeah, it will show in our tracker.
Assigning
VR.
VR.
There we go.
Yeah.
So all of these things which are assigned to me for now. Some of them are Orca issues, but they have been reported on GPDB because that's one of the biggest consumer of Orca.
Yeah.
That is a very good place to go start taking a stab at it.
Does that answer?
Does anybody need to sign a contract or any legal document to contribute?
Yes. Basically, you have to sell your firstborn. No, just kidding. There is a contribution license agreement. We also have a bot that checks whether you have signed it before we will look at your code. So it's really easy. It takes 4 clicks. So.
Any other questions?
We actually didn't
We
take
can,
We just won't merge it.
yeah. We can actually look at that rule in this. Oh, this is maybe not large enough.
Oh.
Yeah. There we go. That's large. Right, we can look at the code a little bit if we want to go a little bit further, right? Remember in the slide we say, hey, we add a rule, we actually have that rule here. It's called split GP AGG, right? And then if you look at it, this is the header file for this rule, which is like f-compatible. This one saying, hey, I'm not produced by myself, and also there's another one, distinct qualified aggregate. Even not produced by distinct qualified aggregate, then I can apply to this rule. And this is the transform, the definition of transform, and then we'll go to the actual implementation of it. And let me think, is there anything else here? Okay, we can go to the class. Oops. Right. So this is actually on the slide where we have the expressions. The expression is actually here, which is exactly the same. So it's very easy to write a pattern. If you get used to all these, ignore all these things, then it's very easy to pattern of the tree you want.
Question.
Yeah.
Can you elaborate on this difference between this leaf and a tree?
Right. That's a
See
very
pattern.
good question.
Yeah. So C pattern tree means that you are pulling. It's taking the project list, which is all of your aggregates. So it's going to pull the whole tree up. A leaf meaning you could have an arbitrarily large subtree, but you don't care about it. You're going to pretend it's a leaf node. So the C pattern leaf will just get the root of it,
Get the root.
and C pattern tree will get the whole tree underneath it.
Right.
Because when you're going to split your aggregate, you need to know what is that. It could be sum of A plus B, or sum of A minus B, or it could be count of distinct. So there is an arbitrarily long tree there. So you need to get all because you need to split it.
I actually have no idea what's happening here. No, like we make some pattern here, great,
Yes.
but what happens?
So what happens is that so this says that, oh, whenever you touch, when you go into what this is trying to tell you is to say, if you go and in memo, you touch a group expression that has on a logical operator, logical ag, and it has two nodes, or like leaf and tree. Ignore what it is. It says then what I want you to do is to trigger this, and the input of that transformation will be get the whole scalar tree out and get me the top of the relational child. So that's the pattern it's trying to tell you to the transformation. So once you register the transformation, at basically how the transformation works is it goes through the memo for each group. It looks at an operator and says, hey, what can I apply on you? And then it says, oh, I can apply, you're a group by, so I can apply the split group by. Okay, does it match? And so it tries to check the pattern and then says, oh, I'm going to get the whole scalar tree and I'm going to get the root of the leaf. So.
Right. And add on that, that going to the implementation of the transform, right? So this expression is where we match the pattern. And once we handle this one, we know, once we see PXPR, I know the operator from this expression has to be the logical group by aggregate. So that one match them. And now you see my first child is whatever that written operator is. And then my second child is a scalar, right? In the pattern, I say this is a scalar, which is my projection list. So based on that pattern, I know how I can extract the information I need. Then we start to do the massage. Remember, we want to split it. So in here, basically we say we want to split the projection list into local part and the global part. And I'm just skimming through it, and then basically I want, this is all the column references and everything, and you just go down here. I construct a local aggregate expression, which is using still a logical group by aggregate. And I have my children, which is a relation, and I have my local projection list. And then I can construct aggregate, and it's also a logical group by. And in here I say my children is actually the local I just created. And then I have my global projection list. So in this way, basically, one input of one group by aggregate is split into two group by aggregate. And then at the end, we say the result actually has this one as a result. Yeah.
And a transform can have multiple results.
Correct.
So if you want to take a look at that, you please look at splitting DQA.
Yes. So X form split DQA and make it bigger. And here in the transformations, this is we say first alternatives, I put in the result, and then keep moving on, and I have second alternative, I put in the result, and then we have third alternatives, I put in the result. And eventually, all these different transformations will be costed and evaluated and see which one is the best one.
So what I find amazing working in Orca is everything is, when you're trying to add a transformation, you're only looking at adding a transformation. The engine will take care of costing, the engine will take care of statistics, the engine will take care of when to apply it, whom to apply it, all of those things. You just focus on writing the transformation, writing the patterns that you want to look at. And if you're going to go add a pre-processing step, all you need to focus on is writing a pre-processing step. Rather than, there is no global state to maintain, everything is compartmentalized. So you can focus on contributing in a very small area. So it does not look like this mammoth code base. So that is very good for contributing, especially if you don't want to deal with understanding the whole optimizer. So I would encourage just to go to these two examples and tinkering with this transformation and see what happens. That's a very good starting point.
A question for those who would like to contribute. Are there some documents which gives us more details about it, except what you mentioned earlier in your presentation? And like the coding standard here appears to be following a different nomenclature. Is there any guidelines which you suggest for?
Coding standards is a suggestion, it is not a rule. If contributors can definitely follow their own, and whenever, so all code changes go through pull request. We'll definitely encourage to keep some consistency, but that is not a hindrance for contributing.
Right.
Right, it is. If you touch a file, make sure your code looks like the surrounding lines.
But if you don't, we will comment on the pull request. So.
Right, for the people who want to know more about the ORCA, we mentioned one paper, right? But to understand like mini-DOM, to understand certain rules we write, there are different papers published. So in the slide deck, actually there are a lot more papers, more background, and also including the mini ideas, like how we can test. They're all published in certain papers, so that will help people understand the design, the reasoning behind it.
So in addition, there is also a blog. This actually brings up a good question to do for us. We wrote a blog post of how to profiling Orca. That's in the Pivotal blog. So all of these we can actually put it up in the GitHub as links that people can go access.
I think you also pointed out that what we're missing here is we didn't quite publish like a contributing guide, like a lot of other more popular projects. So as we get more and more attention, we'll just like, I think we'll just be more ready for that. So we'll probably just publish more of those like in the coming days, months, years. I don't know. I don't think promise.
Great. Good.
Did anyone like
Yeah.
post stuff on YouTube or?
All right,
I
cool.
haven't.
Thank you.